Hey guys, tonight we're going on a journey, a long, slow, and impossibly ancient journey, back to the very beginning. Close your eyes for a moment. Can you feel the soft weight of your blanket, the steady rhythm of your breath? Now imagine that you are floating, not in a soft, warm bed, but in the cold, empty darkness of space. Look out into the void. There's nothing but scattered dust, a few gas clouds, and the silent, patient glimmer of distant stars. This is where our story begins, long before the sun had even fully ignited. Long before there was any hint of a planet called Earth. It's a place where you would certainly not survive for even a second. The pressure would crush you, the cold would freeze you, and the radiation would tear you apart. A truly unforgiving cradle. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you're up for it, let me know where you are in the world and what time it is for you. Knowing that we're all listening together across different places and different times makes this shared journey even more special. Now let's begin to travel through time, not as a swift, jarring leap, but as a gentle drift. We're going to watch a new world form from nothing but a whisper of gravity and a swirling cloud of cosmic leftovers. The journey starts not with a bang, but with a slow, almost imperceptible gathering. Think of a vast cosmic tapestry woven from threads of hydrogen and helium, laced with the heavier elements forged in the hearts of long-dead stars. This is our nebula, a nursery for a star and its future children. Gravity, that ever-present sculptor of the cosmos, begins its patient work. It's an invisible hand reaching out to pull the threads of this tapestry closer together. It finds tiny imperfections in the cloud's density, a slightly thicker patch here, a more concentrated swirl there, and it begins to amplify them. It's a bit like the way a single ripple in a pond can grow into a wave. As these patches of gas and dust get denser, their gravitational pull strengthens, and they begin to attract even more matter. This is a runaway process, a slow avalanche of particles that will eventually birth a star. At the very center of this swirling cloud, the pressure and temperature begin to climb dramatically. It becomes a furnace, an embryonic star-to-be, known as a protostar. The light and heat it emits push back against the incoming matter, but gravity is relentless. It's a tug-of-war that goes on for millions of years. Eventually, the core of the protostar becomes so hot and so dense that something incredible happens. Nuclear fusion ignites. Hydrogen atoms are slammed together with such force that they fuse, creating helium and releasing an immense burst of energy. Our sun is born. The sudden, powerful stellar wind, it unleashes a stream of charged particles, begins to blow away the remaining gas and dust from the inner part of the nebula, but not before a new secondary act of creation begins. Around our young blazing star, a flat spinning disk of leftover material forms. This is our protoplanetary disk, and it is here that our story really gets personal. The disk is not uniform. It's a swirling sea of rock metal, ice, and gas. Think of it as a vast cosmic carousel with different materials congregating at different distances from the sun. The inner part of the disk is too hot for volatile materials like ice and gas to condense, so it's dominated by heavier, more refractory materials like silicates and iron. The outer parts, however, are cool enough for ices to form, making them much more massive and giving rise to the gas giants we know today. We are interested in the inner disk, the part where our own planet will eventually form. Here, tiny grains of dust the size of a sand particle begin to collide. At first, these collisions are gentle, and the particles simply stick together, held by electrostatic forces, much like dust bunnies gathering under a bed. This process, known as accretion, is a bit of a cosmic lottery. Some collisions are destructive, shattering the particles back into smaller bits, but over time, the constructive ones win out. The particles grow from dust grains to pebbles, from pebbles to rocks, and from rocks to boulders. As they grow, their own gravitational pull becomes significant. This is a crucial turning point. Once these objects reach a certain size, perhaps a kilometer or so across, they are no longer just floating debris. They are planetesimals. These planetesimals are the building blocks of our solar system. They begin to dominate their local gravitational neighborhoods, sweeping up the smaller bits of rock and dust around them. Collisions between these planetesimals are far from gentle. They are violent high-speed impacts that can shatter objects, or if the angles and speeds are just right, merge them into larger bodies. Imagine a scene of cosmic billiards, but with objects the size of mountains and speeds measured in thousands of kilometers per hour. The early inner solar system was a chaotic, violent place. The planetesimals grew, and a handful of them grew faster and larger than the rest. These are our planetary embryos, the early versions of Mercury, Venus, Mars, and of course Earth. They were massive enough to have their own gravitational fields, and they began to clear out their orbital paths, either by absorbing the smaller planetesimals or flinging them into new, often destructive trajectories. Our young Earth at this point was a sphere of fiery molten rock. It was constantly being bombarded by these remaining planetesimals, an event known as the Late Heavy Bombardment. We can see the evidence of this era today on the surface of the Moon, which is pockmarked with craters from this violent time. Earth, being geologically active, has erased most of its own craters from this period, but the Moon, a silent witness to our planet's formation, holds the scars of that chaotic time for all to see. The constant bombardment wasn't just destructive, it was also constructive. Each impact added mass and energy to our growing planet. The energy from these collisions, combined with the decay of radioactive elements within the planet's core, kept the entire world in a molten state. Our early Earth was not a solid sphere. It was a churning ocean of liquid rock, a sea of magma hundreds of kilometers deep. In this fiery liquid, a process called differentiation began to occur. Denser elements like iron and nickel sank toward the center of the planet, forming the core. Lighter elements like silicates floated to the surface, forming the initial mantle and crust. This process of differentiation is a fundamental concept in planetary science, and it's a bit like what happens when you let a container of mixed salad dressing sit for a while. The heavier oils and spices sink, while the lighter vinegar rises to the top. On a planetary scale, this simple principle created the layered structure of Earth, the solid inner core, the liquid outer core, the thick mantle, and the thin floating crust we live on today. But something else happened during this early chaotic period that would have a profound and lasting effect on our planet and on us. It's a theory known as the giant impact hypothesis, and it explains the origin of our Moon. The idea is that a Mars-sized planetesimal, sometimes called Theia, collided with the young Earth. It wasn't a head-on collision, but a glancing blow and impact so powerful it would have vaporized both bodies. The immense energy of the collision flung a massive amount of molten and vaporized material into orbit around Earth. Over time, this debris coalesced again through accretion to form our Moon. The evidence for this is compelling. The Moon's composition is very similar to Earth's mantle, but it's largely depleted of iron, which makes sense if the impact happened after Earth had already differentiated and its iron core had formed. Furthermore, the Moon's orbit and its rotation speed are consistent with such a massive collision. This single cataclysmic event not only gave us our Moon, but also fundamentally changed our planet. The impact likely tilted Earth on its axis, giving us our seasons, and the Moon's gravitational pull would later become a powerful force, stabilizing our planet's tilt and creating the tides. This early Earth, with its fiery surface and its brand new Moon, was still a long way from being a habitable world. The atmosphere, if you could even call it that, was a toxic mix of volcanic gases, carbon dioxide, nitrogen, and water vapor with no free oxygen. The surface was a roiling inferno, constantly reshaped by volcanic eruptions and the lingering impacts of meteorites. The days were much shorter, perhaps only 5 or 6 hours long, because of the rapid spin of the young planet. And the Moon, being much closer to Earth, would have dominated the sky, appearing far larger and brighter than it does today. This is the end of the Hadean Eon, a time of intense heat and cosmic violence. The name Hadean comes from Hades, the Greek god of the underworld, and it's a fitting name for a period when our planet was a hellscape. We've watched a world form from a cloud of dust, we've seen it get smashed into a fiery pulp, and we've witnessed the birth of its silent companion in the sky. It's a chaotic, beautiful, and utterly alien beginning. And yet, this violent chaos was the necessary prelude to the gentle, life-giving world we now inhabit. The slow cooling of this fiery planet is the next chapter, a period that will eventually allow for the formation of liquid water, the most fundamental ingredient for life as we know it. And this raises an interesting question. If the conditions for forming a planet are so common throughout the universe, how often do all the necessary factors, the right type of star, the correct distance, the powerful but non-destructive impacts line up just right to create a world that can not only sustain life, but also hold on to it for billions of years? The truth is, we don't really know for sure, and the rarity of our own existence might be one of the greatest mysteries of all. We left our young Earth as a furious molten sphere, a truly inhospitable world, still reeling from the cosmic violence of its birth. But even in this chaos, a gentle and relentless process had begun cooling. The heat generated by impacts and radioactive decay was immense, but the planet was a big place, and it had a vast, cold universe to radiate that energy into. Slowly, inexorably, the surface of this fiery ocean of magma began to solidify, much like a thin skin of ice forming on a cooling pot of water. This first crust was fragile, a patchwork of volcanic rock constantly being broken and remelted by the violent forces below. It was a time of unending volcanic activity, a world covered in a thick, choking atmosphere of steam carbon dioxide and other gases belched out from the planet's interior. This is the heart of the Hadean Eon, a period named after Hades, the Greek god of the underworld, a fitting name for this era of fire and fury. Imagine a landscape of unending red and orange. Volcanoes, not just isolated peaks, but vast fissures and cracks in the planet's surface constantly spew lava and gas into the air. The sky is not blue. It's a deep, murky red, filled with volcanic ash and steam. The sun is a pale, distant ghost, its light struggling to penetrate this thick, toxic blanket. The air pressure is immense, perhaps 270 times what we experience today, a crushing weight that would instantly flatten us. And yet, beneath this brutal exterior, the groundwork for a new world was being laid. The crust, though constantly being recycled, was thickening. This is the birth of plate tectonics, a process that is as fundamental to Earth's story as gravity itself. At first, the crust was probably broken into many small mobile plates. Convection currents in the molten mantle below, a bit like the slow roiling movement of a thick soup being heated from the bottom, drag these plates around. They collided, they subducted one plate, sliding under another, and they were pulled apart, creating new crustal material. This process, which continues to this day, is a vital part of Earth's self-regulation. It recycles elements, builds mountains, and creates the very continents we live on. But the most critical change was happening in the atmosphere. The constant volcanic outgassing filled the air with water vapor. And as the planet continued to cool, that steam began to condense. It's a simple idea, but the scale of it is almost impossible to grasp. For millions of years, the sky was a giant pressure cooker. Eventually, a tipping point was reached, and the temperature dropped below the boiling point of water. The result was not a gentle rain. It was a torrential downpour of biblical proportions, a deluge that would have lasted for thousands of years. This was the moment the oceans were born. The oceans weren't born pristine and blue. They were a hot, acidic, and probably greenish-brown soup, filled with dissolved minerals from the newly formed rocks. But they were water, and that was the key. Water is an incredible solvent, and it's the medium in which all the subsequent chemical and biological reactions would take place. It's the ultimate canvas for life. This is the transition from the Hadean to the Archean eon, a time named for the Greek word arche, meaning beginning. It is a time of beginnings in the truest sense of the word. The creation of the oceans also had a profound effect on the planet's atmosphere. Carbon dioxide, which was so abundant in the Hadean atmosphere, began to dissolve into the new oceans. This is a simple chemical process. CO2 reacts with water to form carbonic acid. This process, a bit like adding fizz to soda water, would have made the early oceans very acidic. But over time, that carbonic acid reacted with minerals in the newly formed crustal rocks, pulling the carbon out of the water and locking it away in the form of carbonate rocks such as limestone. This is a fundamental part of Earth's long-term carbon cycle, and this first great drawdown of carbon from the atmosphere helped to further cool the planet, making it even more hospitable to life. While the planet was cooling and the oceans were forming, something even more profound was taking place in the hot, mineral-rich waters. The scientific term is abiogenesis, the emergence of life from non-living matter. This is perhaps the greatest scientific mystery of all, a puzzle that still captivates and confounds us. We don't have a single definitive answer, but we have some fascinating ideas. One of the leading theories involves deep-sea hydrothermal vents. These are cracks in the ocean floor where geothermally heated water, rich in minerals and chemicals, spews out into the cold ocean. Imagine a world without sunlight, a world of perpetual darkness at the bottom of a new ocean. And yet these vents are oases of chemical energy. The temperature gradients, the flow of chemicals, and the protective porous rock structures of these vents could have provided the perfect conditions for complex organic molecules to form. 2. Think of it as a microscopic chemical factory. Carbon atoms, hydrogen atoms, oxygen, nitrogen. All the building blocks of life are present in the primordial soup. In the protective nooks and crannies of these vents, these simple molecules could have been concentrated and subjected to the energy of the hot water. The result, over millions of years, could have been the spontaneous formation of more complex molecules like amino acids and nucleotides, the very building blocks of proteins and DNA. We know from an experiment conducted in the 1950s by Stanley Miller and Harold Urey that the raw materials of life can be created from a primordial soup of gases and a spark of electricity, mimicking what scientists thought the early Earth's atmosphere was like. While our understanding of the early atmosphere has changed, the core idea that life's building blocks can form spontaneously under the right conditions remains a powerful one. But here's the most mind-bending part of the whole story. Forming the building blocks is one thing. Assembling them into a self-replicating organism is another. This is the leap from chemistry to biology. One of the most intriguing hypotheses involves something called the RNA world hypothesis. DNA, the genetic blueprint for life as we know it, is a complex molecule that requires a whole host of proteins to replicate itself. But RNA, a simpler cousin of DNA, can act as both a genetic blueprint and as an enzyme, a catalyst for chemical reactions. In the RNA world hypothesis, RNA was the first genetic material, a simpler system that could both store information and replicate itself. Over time, this RNA world gave way to the more stable and efficient DNA-based life we see today. The first forms of life were almost certainly single-celled organisms, simple prokaryotic cells that lacked a nucleus. They were nothing more than a tiny bag of chemicals, a cell wall containing RNA or DNA, and a few basic proteins. They lived in the hot anoxic oceans, surviving on the chemical energy provided by the vents or by consuming other organic molecules in the primordial soup. They were the ultimate minimalists, and they were everywhere. A fascinating and often overlooked truth about these early life forms is that they existed in a world that would be utterly toxic to us. The atmosphere had no free oxygen. In fact, for these first organisms, oxygen was a deadly poison, a highly reactive gas that would have destroyed their delicate chemical machinery. This is a concept known as the Great Oxidation Event, and we'll get to it later. But for now, remember that the first life on Earth was an anaerobic world, a whisper of biology in a great ocean of chemistry. This raises a deep philosophical question. If the conditions for abiogenesis are met, is the emergence of life inevitable? Or was it an incredibly lucky one-in-a-trillion cosmic accident? The truth is, we don't know for sure. It's a mystery that lies at the intersection of chemistry, biology, and the sheer luck of the cosmos. Scientists still wonder if life on Earth is a unique phenomenon, or if the universe is teeming with life that has in a million different ways emerged from non-living matter. And so, as the Hadean Eon gives way to the Archean, our story shifts from geology to biology. The fire and fury of the early Earth gave way to the gentle, patient persistence of life itself. The stage is set. The oceans are in place. The crust is thickening, and in the dark corners of the deep, a new story is beginning to be written, one that will forever change the face of the planet. The Archean Eon, the age of beginnings, was a world of deep oceans and barren continents, a place where the colors we associate with life, green-blue, and a host of others, were almost entirely absent. The sky was still a murky red, the land a desolate expanse of volcanic rock, and the oceans were a soupy mix of hot, mineral-rich water. And yet, this was the crucible of life. The first organisms, those tiny anaerobic cells we spoke of, were beginning to proliferate in this chemical garden. They were simple, but they were the pioneers, the quiet architects of everything that would follow. These early life forms were prokaryotes, single-celled organisms that lacked a nucleus and other complex internal structures. They lived in a world without free oxygen, and they had to find a way to get energy from their surroundings. Most of them were chemoautotrophs, meaning they got their energy from chemical reactions. They lived by eating the minerals and chemicals around them, particularly those found near the deep-sea vents. For them, a world without sunlight was no obstacle. They were in a way the original inhabitants of a planet that was still a work in progress, and their existence was a testament to life's incredible ability to find a way no matter how hostile the environment. But something much more significant, a revolution on a planetary scale, was on the horizon. The key to this revolution was a new form of energy production, one that would unlock the power of the sun itself. This was the invention of photosynthesis. Think of it as the ultimate upgrade. Instead of relying on the limited and localized chemical energy from vents, these new organisms could tap into an almost infinite power source, starlight. The earliest forms of photosynthesis were anoxygenic, meaning they didn't produce oxygen. They used other chemicals like hydrogen sulfide in their process. But eventually, a group of bacteria evolved a new, more efficient type of photosynthesis, one that used water as its electron donor. These were the cyanobacteria, and their appearance marks one of the most pivotal moments in Earth's history. These tiny, simple organisms, often called blue-green algae, began to thrive in the sunlit upper layers of the oceans. They were small, but their numbers were staggering. Imagine them a silent, microscopic army floating in the warm, shallow seas. As they photosynthesized, they performed a simple but world-changing act. They consumed carbon dioxide and released oxygen as a waste product. This oxygen was, as we mentioned before, a deadly poison to most of the life on the planet at the time. It was a new, highly reactive gas that would have wreaked havoc on the delicate chemical systems of the anaerobic organisms. This is one of the greatest ironies in Earth's story. The very breath of life for us was for billions of years a toxic, dangerous pollutant. At first, this newly produced oxygen didn't build up in the atmosphere. It immediately reacted with the abundant iron dissolved in the ancient oceans. The oxygen would rust the iron, causing it to precipitate out of the water and fall to the ocean floor. Over millions of years, this process created massive deposits of banded iron formations, or BIFs. These are some of the oldest and most widespread rock formations on Earth, and they are a stunning geological record of the very first breaths of our oxygenated world. We can still see these alternating red iron-rich and gray iron-poor layers today, a beautiful and silent testament to a planetary shift of unimaginable proportions. They are, in a sense, the planet's first diary, a record of the slow, patient work of these tiny architects. As the available iron in the oceans was slowly consumed, the oxygen had nowhere else to go. It began to dégage from the oceans and accumulate in the atmosphere. This marked the beginning of the Great Oxidation event, also sometimes called the oxygen catastrophe. For the anaerobic life that had dominated for so long, this was a global disaster. The vast majority of these organisms were either wiped out or forced into tiny oxygen-free corners of the world, like deep-sea sediments or anaerobic swamps. The planet was, in a sense, poisoning itself to death in order to create a new oxygen-rich world. This massive influx of oxygen also had another profound effect. It began to react with the methane in the atmosphere. Methane is a very powerful greenhouse gas, and its presence had been helping to keep the planet warm despite the sun being much dimmer in those early days, a concept known as the faint young sun paradox. The oxygen reacted with the methane, converting it to carbon dioxide and water, which are less effective at trapping heat. This led to a dramatic cooling of the planet, a period of global glaciation that some scientists believe was the first of the great snowball Earth events. This is a wonderful example of a strange, little-known scientific fact, a chemical reaction on a microscopic level. The release of oxygen by bacteria could trigger a global climate change, plunging the entire planet into a deep freeze. It shows how interconnected all the systems of our planet truly are, from the smallest cell to the largest ice sheet. But the new oxygen-rich atmosphere was also a gift and unlocking of new evolutionary potential. Oxygen is a much more efficient way to get energy from food than anaerobic processes. It's like switching from a small sputtering engine to a high-performance one. Life could now grow larger, become more complex, and move with more energy. The stage was being set for the next great leap in the story of life. The Archean Eon was also a time of significant geological change. Plate tectonics, that slow grinding engine of the planet, was beginning to form the first small continents called cratons. These were the stable cores of what would become our modern continents. They were small and probably didn't look like the continents we see today. They were island-like, but they were the first solid, long-lasting pieces of land to rise above the waves. Think of the Earth's crust as a vast puzzle-like floor. In the Hadean, the pieces were small and constantly being smashed together and recycled. In the Archean, some of these pieces began to stick together, forming larger, more stable blocks. This is a crucial concept, as the formation of these stable cratons would eventually allow for the evolution of land-based life. And this raises an interesting question. Was the evolution of photosynthesis an inevitable outcome of life on a planet with a star? Or was it a lucky break, a single chance occurrence that happened to be successful and went on to completely reshape the entire world? The truth is, we don't really know for sure. The path from a chemosynthetic world to a photosynthetic one is a massive evolutionary leap, and the fact that it happened at all is nothing short of miraculous. So, as the Archean Eon draws to a close, we leave a planet that is utterly different from the one we started with. The atmosphere is no longer toxic, the oceans are no longer a chemical soup, and the land, though still barren, is beginning to take shape. And within those oceans, a new kind of organism is beginning to thrive, an organism that has, through its simple, quiet work, laid the very foundation for everything that we are and everything that we see around us today. The Proterozoic Eon, which means earlier life, was a time of immense slow-motion change. We've moved past the fire and fury of the Hadean and the great biological revolution of the Archean. Now, we enter a period of quiet consolidation, where the pieces of our planet began to settle into place. The first great shift of this era was geological. The cratons, those small island-like continents from the previous eon, began to collide. Driven by the patient, relentless engine of plate tectonics, These smaller landmasses fused together to form the first true supercontinents. The first of these, a sprawling landmass often referred to as Rodinia, was a testament to the planet's evolving geology. Imagine a dance on an unimaginably slow scale. These continents, floating on the viscous mantle below, were constantly in motion. They drifted, they bumped into each other, and they were pulled apart. When they collided, they created massive mountain ranges far grander than anything we see today. These were the first great orogenies, the processes of mountain building, which sculpted the planet's surface in ways we can only imagine. The formation of a supercontinent like Rodinia had a profound impact on the planet's climate and biology. It altered global ocean currents, which in turn affected the distribution of heat. It also created vast, shallow seas on the continental shelves, which would become the nurseries for a new, more complex form of life. The other great shift of this eon was biological. Those single-celled cyanobacteria we talked about were still hard at work pumping oxygen into the atmosphere. The great oxidation event was in full swing, and the air was slowly becoming more breathable. But the real game changer was the evolution of a new kind of cell, the eukaryote. Unlike the simple prokaryotes, eukaryotes had a nucleus to house their genetic material and a host of other complex internal compartments called organelles. This was a monumental leap in biological complexity. It's the difference between a simple single-room workshop and a sprawling factory with specialized machines and separate assembly lines. The exact origin of eukaryotes is another one of those wonderful scientific mysteries, but the leading theory is known as endosymbiosis. It suggests that a larger prokaryotic cell engulfed a smaller one, but instead of digesting it, the two formed a symbiotic relationship. The smaller cell lived inside the larger one, providing a benefit in exchange for protection. Over millions of years, this became a permanent arrangement. Think of the mitochondria in our cells, for example. These are the powerhouses of the cell, and they have their own DNA separate from the rest of the cell's genetic material. This is a powerful clue that they were once independent organisms. A similar process is thought to have given rise to chloroplasts in plant cells. This symbiotic relationship was a masterstroke of evolution, creating a cell that could do more, grow larger, and survive in more complex ways. With the advent of eukaryotes, the door was open for a whole new level of biological organization, multicellularity. For the first time, cells began to work together. This wasn't just a random collection of cells. They were coordinated, specialized, and interdependent. The first multicellular organisms were simple, probably small colonies of cells, but they were the first glimmer of the complex life forms we see today. They were the first to show the division of labor that is the hallmark of all complex life, where some cells do one job and others do another. As the Proterozoic eon drew to a close, the supercontinent of Rodinia began to break apart. This rifting a bit, like a tectonic divorce, created new coastlines and new shallow seas, which were teeming with this new, more complex life. However, this period of tectonic change also had a dramatic and catastrophic effect on the planet's climate. The breakup of Rodinia led to a period of intense weathering, which drew large amounts of carbon dioxide out of the atmosphere. As we discussed before, carbon dioxide is a greenhouse gas, and its removal from the atmosphere caused a dramatic cooling. This led to a series of global glaciations so severe that the entire planet may have been covered in ice from the poles to the equator. This is the snowball Earth hypothesis, a fascinating and controversial idea. Think of it as the ultimate climate feedback loop. As the planet cooled, more ice formed. Ice is highly reflective, so it bounced more of the sun's energy back into space, causing the planet to cool even more, which in turn created even more ice. It was a vicious cycle that almost froze the planet solid. A little known but intriguing fact about Snowball Earth is the theory of how the planet escaped its icy slumber. The very same volcanoes that built the continents kept erupting. They pumped massive amounts of carbon dioxide into the atmosphere, but the ice-covered oceans couldn't absorb it. The CO2 built up in the atmosphere, and over millions of years, the greenhouse effect became so powerful that it began to melt the ice, a process that would have been sudden and dramatic, like the planet waking from a deep freeze. This raises another one of those great unanswered questions. How did life survive Snowball Earth? Was there enough open water near volcanic vents, or were the organisms simply tough enough to survive the deep freeze? We have some fossil evidence that suggests life did persist, but the details of how are still a matter of scientific debate. It's a powerful reminder that life on our planet is incredibly resilient, capable of surviving the most extreme and catastrophic events. So as we move from the Proterozoic to the next great eon, we leave behind a world that has been utterly transformed. The continents have come together and broken apart. The atmosphere has become oxygen-rich, and life has moved from simple single-celled organisms to complex multicellular creatures. The stage is set for the greatest show in all of Earth's history, the sudden and dramatic explosion of animal life that would come next. The Proterozoic eon was a time of immense slow-motion change. We've moved past the fire and fury of the Hadean and the great biological revolution of the Archean. Now, we enter a period of quiet consolidation where the pieces of our planet began to settle into place. The first great shift of this era was geological. The cratons, those small island-like continents from the previous eon, began to collide. Driven by the patient, relentless engine of plate tectonics, these smaller landmasses fused together to form the first true supercontinents. The first of these, a sprawling landmass often referred to as Rodinia, was a testament to the planet's evolving geology. Imagine a dance on an unimaginably slow scale. These continents floating on the viscous mantle below were constantly in motion. They drifted, they bumped into each other, and they were pulled apart. When they collided, they created massive mountain ranges far grander than anything we see today. These were the first great orogenies, the processes of mountain building, which sculpted the planet's surface in ways we can only imagine. The formation of a supercontinent like Rodinia had a profound impact on the planet's climate and biology. It altered global ocean currents, which in turn affected the distribution of heat. It also created vast, shallow seas on the continental shelves, which would become the nurseries for a new, more complex form of life. The other great shift of this eon was biological. Those single-celled cyanobacteria we talked about were still hard at work pumping oxygen into the atmosphere. The great oxidation event was in full swing, and the air was slowly becoming more breathable. But the real game changer was the evolution of a new kind of cell, the eukaryote. Unlike the simple prokaryotes, eukaryotes had a nucleus to house their genetic material and a host of other complex internal compartments called organelles. This was a monumental leap in biological complexity. It's the difference between a simple single-room workshop and a sprawling factory with specialized machines and separate assembly lines. The exact origin of eukaryotes is another one of those wonderful scientific mysteries. But the leading theory is known as endosymbiosis. It suggests that a larger prokaryotic cell engulfed a smaller one, but instead of digesting it, the two formed a symbiotic relationship. The smaller cell lived inside the larger one, providing a benefit in exchange for protection. Over millions of years, this became a permanent arrangement. Think of the mitochondria in our cells, for example. These are the powerhouses of the cell, and they have their own DNA, separate from the rest of the cell's genetic material. This is a powerful clue that they were once independent organisms. A similar process is thought to have given rise to chloroplasts in plant cells. This symbiotic relationship was a masterstroke of evolution, creating a cell that could do more, grow larger, and survive in more complex ways. With the advent of eukaryotes, the door was open for a whole new level of biological organization, multicellularity. For the first time, cells began to work together. This wasn't just a random collection of cells. They were coordinated, specialized, and interdependent. The first multicellular organisms were simple, probably small colonies of cells, but they were the first glimmer of the complex life forms we see today. They were the first to show the division of labor that is the hallmark of all complex life, where some cells do one job and others do another. As the Proterozoic eon drew to a close, the supercontinent of Rodinia began to break apart. This, rifting a bit like a tectonic divorce, created new coastlines and new shallow seas, which were teeming with this new, more complex life. However, this period of tectonic change also had a dramatic and catastrophic effect on the planet's climate. The breakup of Rodinia led to a period of intense weathering, which drew large amounts of carbon dioxide out of the atmosphere. As we discussed before, carbon dioxide is a greenhouse gas, and its removal from the atmosphere caused a dramatic cooling. This led to a series of global glaciations so severe that the entire planet may have been covered in ice from the poles to the equator. This is the snowball Earth hypothesis, a fascinating and controversial idea. Think of it as the ultimate climate feedback loop. As the planet cooled, more ice formed. Ice is highly reflective, so it bounced more of the sun's energy back into space, causing the planet to cool even more, which in turn created even more ice. It was a vicious cycle that almost froze the planet solid. A little known but intriguing fact about Snowball Earth is the theory of how the planet escaped its icy slumber. The very same volcanoes that built the continents kept erupting. They pumped massive amounts of carbon dioxide into the atmosphere, but the ice-covered oceans couldn't absorb it. The CO2 built up in the atmosphere, and over millions of years, the greenhouse effect became so powerful that it began to melt the ice, a process that would have been sudden and dramatic, like the planet waking from a deep freeze. This raises another one of those great unanswered questions. How did life survive Snowball Earth? Was there enough open water near volcanic vents, or were the organisms simply tough enough to survive the deep freeze? We have some fossil evidence that suggests life did persist, but the details of how are still a matter of scientific debate. It's a powerful reminder that life on our planet is incredibly resilient, capable of surviving the most extreme and catastrophic events. So as we move from the Proterozoic to the next great eon, we leave behind a world that has been utterly transformed. The continents have come together and broken apart. The atmosphere has become oxygen-rich, and life has moved from simple single-celled organisms to complex multicellular creatures. The stage is set for the greatest show in all of Earth's history, the sudden and dramatic explosion of animal life that would come next. The Proterozoic eon, which means earlier life, was a time of immense slow-motion change. We've moved past the fire and fury of the Hadean and the great biological revolution of the Archean. Now, we enter a period of quiet consolidation where the pieces of our planet began to settle into place. The first great shift of this era was geological. The cratons, those small island-like continents from the previous eon, began to collide. Driven by the patient, relentless engine of plate tectonics, these smaller landmasses fused together to form the first true supercontinents. The first of these, a sprawling landmass often referred to as Rodinia, was a testament to the planet's evolving geology. Imagine a dance on an unimaginably slow scale. These continents floating on the viscous mantle below were constantly in motion. They drifted, they bumped into each other, and they were pulled apart. When they collided, they created massive mountain ranges, far grander than anything we see today. These were the first great orogenies, the processes of mountain building, which sculpted the planet's surface in ways we can only imagine. The formation of a supercontinent, like Rodinia, had a profound impact on the planet's climate and biology. It altered global ocean currents, which in turn affected the distribution of heat. It also created vast, shallow seas on the continental shelves, which would become the nurseries for a new, more complex form of life. The other great shift of this eon was biological. Those single-celled cyanobacteria we talked about were still hard at work pumping oxygen into the atmosphere. The great oxidation event was in full swing, and the air was slowly becoming more breathable. But the real game changer was the evolution of a new kind of cell, the eukaryote. Unlike the simple prokaryotes, eukaryotes had a nucleus to house their genetic material and a host of other complex internal compartments called organelles. This was a monumental leap in biological complexity. It's the difference between a simple single-room workshop and a sprawling factory with specialized machines and separate assembly lines. The exact origin of eukaryotes is another one of those wonderful scientific mysteries, but the leading theory is known as endosymbiosis. It suggests that a larger prokaryotic cell engulfed a smaller one, but instead of digesting it, the two formed a symbiotic relationship. The smaller cell lived inside the larger one, providing a benefit in exchange for protection. Over millions of years, this became a permanent arrangement. Think of the mitochondria in our cells, for example. These are the powerhouses of the cell, and they have their own DNA, separate from the rest of the cell's genetic material. This is a powerful clue that they were once independent organisms. A similar process is thought to have given rise to chloroplasts in plant cells. This symbiotic relationship was a masterstroke of evolution, creating a cell that could do more, grow larger, and survive in more complex ways. With the advent of eukaryotes, the door was open for a whole new level of biological organization, multicellularity. For the first time, cells began to work together. This wasn't just a random collection of cells. They were coordinated, specialized, and interdependent. The first multicellular organisms were simple, probably small colonies of cells, but they were the first glimmer of the complex life forms we see today. They were the first to show the division of labor that is the hallmark of all complex life, where some cells do one job and others do another. As the Proterozoic eon drew to a close, the supercontinent of Rodinia began to break apart. This rifting, a bit like a tectonic divorce, created new coastlines and new shallow seas, which were teeming with this new, more complex life. However, this period of tectonic change also had a dramatic and catastrophic effect on the planet's climate. The breakup of Rodinia led to a period of intense weathering, which drew large amounts of carbon dioxide out of the atmosphere. As we discussed before, carbon dioxide is a greenhouse gas, and its removal from the atmosphere caused a dramatic cooling. This led to a series of global glaciations so severe that the entire planet may have been covered in ice from the poles to the equator. This is the snowball Earth hypothesis, a fascinating and controversial idea. Think of it as the ultimate climate feedback loop. As the planet cooled, more ice formed. Ice is highly reflective, so it bounced more of the sun's energy back into space, causing the planet to cool even more, which in turn created even more ice. It was a vicious cycle that almost froze the planet solid. A little known but intriguing fact about Snowball Earth is the theory of how the planet escaped its icy slumber. The very same volcanoes that built the continents kept erupting. They pumped massive amounts of carbon dioxide into the atmosphere, but the ice-covered oceans couldn't absorb it. The CO2 built up in the atmosphere, and over millions of years, the greenhouse effect became so powerful that it began to melt the ice, a process that would have been sudden and dramatic, like the planet waking from a deep freeze. This raises another one of those great unanswered questions. How did life survive? Snowball Earth. Was there enough open water near volcanic vents? Or were the organisms simply tough enough to survive the deep freeze? We have some fossil evidence that suggests life did persist, but the details of how are still a matter of scientific debate. It's a powerful reminder that life on our planet is incredibly resilient, capable of surviving the most extreme and catastrophic events. So as we move from the Proterozoic to the next great eon, we leave behind a world that has been utterly transformed. The continents have come together and broken apart. The atmosphere has become oxygen-rich, and life has moved from simple single-celled organisms to complex multicellular creatures. The stage is set for the greatest show in all of Earth's history, the sudden and dramatic explosion of animal life that would come next. After the long, slow, and often quiet history of the Proterozoic, a seismic shift occurred. The planet, having gone through the deep freeze of snowball Earth, was now awakening to a new era, a time of unprecedented change and biological innovation. This is the Cambrian explosion, a name that perfectly captures the sudden and dramatic diversification of life that took place about 541 million years ago. Imagine the planet as a stage that had been set for billions of years. The atmosphere was oxygenated, the oceans were full of nutrients, and the genetic groundwork of eukaryotes and multicellularity was in place. And then, all at once, the curtain rose. Before, the Cambrian life was dominated by simple, soft-bodied creatures. The fossil record, remember, is a notoriously incomplete story. It's like a book with most of its pages torn out. But what we do find from the period just before the Cambrian, the Ediacaran, are fossils of strange quilt-like organisms. They lacked a hard skeleton, so their preservation is a rare and delicate thing. But in the blink of a geological eye, these simple forms gave way to a riot of new life. Almost all the major animal body plans, or phyla, that we know today appeared in the fossil record within a relatively short span of time, a mere 20 to 25 million years. The oceans became a bustling, competitive new world. Creatures developed hard body parts for the first time, shells, skeletons, and exoskeletons. Think of it as a biological arms race. The evolution of a hard shell, for example, was a powerful defensive innovation, a suit of armor against the first predators. In response, predators developed their own weapons like claws and teeth. The appearance of eyes was another game changer. An eye is a window into the world, an incredible tool for both hunting and evading. This new ecological dynamic, the constant pressure of predator and prey, drove evolution at an astonishing pace. One of the most iconic creatures of the Cambrian explosion was the trilobite. These were arthropods, distant cousins of modern insects and crustaceans with a hard segmented exoskeleton. They scuttled across the seafloor and were one of the most successful groups of animals for hundreds of millions of years. Another fascinating fossil is Anomalocaris, which means strange shrimp. It was a formidable predator with large compound eyes and two spiny claws in front of its mouth. It was, for its time, the apex predator of the Cambrian seas, a truly alien creature that shows just how different and experimental early animal life was. The Cambrian explosion is one of those great mysteries that still has scientists wondering. What triggered it? There are several theories, and the truth is probably a combination of them all. The increased oxygen levels in the atmosphere and oceans, a legacy of the Proterozoic, would have allowed for more complex energy-demanding organisms to evolve. The development of new genetic toolkits, the genes that control the body plan of an organism, may have unlocked a new level of evolutionary potential. And as we just discussed, the very act of having predators and prey would have created an intense selective pressure for new forms and defenses. It is a curious and little-known fact of the Cambrian explosion that the variety of animal phyla was actually greater during this time than it is today. It was a time of evolutionary experimentation where life was trying out a dizzying array of body plans, some of which were wildly successful, but many of which eventually died out. The history of life is not a steady march of progress, but a long series of glorious successes and spectacular failures. This sudden burst of life raises a great philosophical question. Why did life take so long to get going? For more than 3 billion years, life was nothing more than a microscopic whisper. And then, in a flash, it blossomed into the complex, diverse world we see in the fossil record. Why the long wait? The answer may lie in the combination of those factors we just mentioned. The planet needed to be stable, the atmosphere needed to be just right, and the genetic toolkit had to be in place. All these ingredients had to be prepared before the great banquet of life could begin. And so, as we leave the Cambrian period, we leave a world that is now alive in a way it never was before. The seas are teeming with creatures, the first food chains are being established, and the long, slow, patient work of evolution is beginning to produce the dazzling variety of forms that will eventually lead to everything from a small fish to the thinking, dreaming mind that is listening to this story right now. The Cambrian explosion filled the oceans with a dazzling array of life, but the land remained a silent, desolate place. It was a world of barren rock, devoid of the vibrant greens and teeming life we associate with continents today. But just as the oceans had been waiting for the right conditions, so too was the land. The move from water to dry ground was one of the most challenging evolutionary transitions in Earth's history, a perilous journey that required a whole new set of biological innovations. The first pioneers to venture onto land were not animals but tiny, unassuming life forms that we often take for granted: plants and fungi. The fossil record for this period is sparse, a testament to the fragile, soft-bodied nature of these early organisms. But we can infer their presence and their methods. Fungi, which form a symbiotic relationship with plant roots, were likely the first to make the move. They are, in a sense, the ultimate recyclers, capable of breaking down rock and organic matter. This ability would have been crucial for creating the first soils, the very foundation of a terrestrial ecosystem. The first land plants, probably little more than mosses and liverworts, were confined to damp coastal areas. They had no roots to anchor themselves or to absorb water, and they had no internal vascular system to transport water and nutrients. They were literally just a mat of green cells clinging to the shore. But their very existence was a monumental achievement. They had to develop a way to prevent themselves from drying out, which they did with a waxy outer layer called a cuticle. They also had to find a way to reproduce without being in water, which they did by using spores, tiny packets of genetic material that could be carried on the wind. But the real breakthrough came with the evolution of vascular plants. This was a pivotal moment, a bit like the invention of plumbing for a biological system. Vascular plants developed an internal system of tubes, the xylem and phloem, that could transport water and nutrients from the ground to the rest of the plant. This allowed them to grow taller, to stand upright, and to compete for the sunlight that was now in abundant supply on the land. With roots to anchor them and a vascular system to support them, the first forests could begin to take shape, transforming the face of the planet forever. As the plants were slowly, patiently colonizing the land, the first animals were also making their tentative steps onto dry ground. These were not the large, charismatic creatures we think of today, but arthropods, insects, spiders, and centipedes. They had a distinct advantage, a pre-existing exoskeleton that provided both support and protection from drying out. The first land animals were likely scavengers or herbivores, feeding on the mats of algae and the early plants that had already established themselves. The appearance of these animals marks the beginning of the first terrestrial food chains, a quiet, almost invisible ecosystem taking root in the silent landscape. A little known but fascinating fact is the potential role of the ozone layer in this transition. The oxygen that the cyanobacteria had been pumping into the atmosphere for hundreds of millions of years was now beginning to accumulate in the upper atmosphere. There it was hit by ultraviolet radiation from the sun, which caused some of the oxygen molecules O2 to split and reform as ozone O3. This ozone layer was a protective blanket shielding the surface of the planet from the sun's most damaging rays. Without it, the land would have been a deadly radiation-scorched zone, and the colonization of the continents might never have happened. This brings up another one of those deep philosophical questions. Was the colonization of the land an inevitable consequence of an oxygenated atmosphere and a protective ozone layer? Or was it a matter of a few lucky breaks, a few key evolutionary innovations that, once they occurred, opened the floodgates for a whole new way of life? The truth is, we don't really know for sure. The path from a water-bound existence to a terrestrial one is fraught with challenges, and the fact that it happened at all is a testament to the relentless problem-solving power of evolution. So, as we move into the Devonian period, sometimes called the Age of Fishes, we can see a world that is beginning to look a little more familiar. The oceans are teeming with a dazzling variety of fish, including the ancestors of all vertebrates, and the land, once a barren rock, is now beginning to be covered in the first primitive forests. This quiet, often overlooked transition from water to land was the necessary prelude to the age of giants that would come next, an era of soaring trees, giant insects, and the very first vertebrates to walk on dry ground. The colonization of the land by plants and the first arthropods was a slow, patient process, but it set the stage for an era of staggering growth. This is the Carboniferous period, which began around 359 million years ago, a time so named because it gave us the vast deposits of coal we use today. It was a world of verdant, sprawling jungles and immense, swampy forests. Imagine a landscape dominated by giant ferns, club mosses, and horsetails, some of which grew to the size of modern trees. These were not the flowering plants we know today. They were a more primitive, spore-bearing kind of vegetation. The reason for this immense growth was twofold. First, the climate was warm and humid, creating the perfect conditions for these plants to thrive. Second, there was a crucial evolutionary bottleneck. The fungi and microorganisms that we now rely on to break down dead wood and plant matter had not yet evolved to a point where they could effectively decompose the complex polymer in wood called lignin. This meant that when these giant trees and plants died, they simply fell into the waterlogged swamps and were buried, preserving their carbon instead of releasing it back into the atmosphere. This is a crucial concept, as this buried compressed carbon is what eventually became the coal, oil, and natural gas that powers our modern world. It is a little known but powerful truth that our industrial civilization is, in a sense, running on the sunlight of a long-dead era. The abundant plant life had a profound effect on the atmosphere. The sheer volume of photosynthesis pulled an immense amount of carbon dioxide out of the air and, in turn, released a massive amount of oxygen. The atmospheric oxygen levels during the Carboniferous are thought to have been the highest in Earth's history, perhaps as high as 35% compared to the 21% we breathe today. This had a dramatic effect on the life that was now inhabiting the land. This brings us to a strange and wonderful fact about this period. The insects were giant. With so much oxygen in the air, the size of an arthropod's respiratory system was no longer a limiting factor. The ancient dragonfly, Meganeura, had a wingspan of up to 2.5 feet. Millipedes like Arthropleura could grow to be over 6 feet long. Imagine a dragonfly the size of a hawk or a millipede the size of a human. These were the true giants of the Carboniferous land, a testament to the power of a single atmospheric variable to reshape an entire ecosystem. Meanwhile, in the swamps below, a crucial transition was taking place. Fish with fleshy lobed fins began to adapt to a life on land. The transition from fish to tetrapod, the first four-limbed vertebrates, is a beautifully documented story in the fossil record. The fish Tiktaalik, with its strong arm-like fins and a flat head with eyes on top, is a perfect transitional fossil, a snapshot of evolution in action. Its descendants, the amphibians, were the first vertebrates to truly colonize the land, though they were still tied to the water for reproduction, much like a frog today. The Carboniferous was also a time of significant geological change. The continents were once again beginning to come together to form a new supercontinent, Pangaea. This slow grinding process created vast, towering mountain ranges and reshaped the global climate. The Hercynian orogeny in Europe and the Appalachian Mountains in North America are both legacies of this period of intense tectonic activity. And this raises an interesting question: was the immense plant growth of the Carboniferous a lucky break, or was it an inevitable outcome of a planet with abundant water and a slowly evolving ecosystem? The truth is, we don't really know for sure. The combination of high humidity and oxygen-rich atmosphere and the inability of decomposers to break down lignin created a perfect storm for the formation of these great forests. It was a unique set of circumstances that gave us both the fuel for our civilization and the giant insects of our nightmares. So, as we leave the Carboniferous period, we leave a world that is now both green and dangerous. A world of towering trees, giant insects, and the first tentative steps of vertebrates onto dry ground. The stage is set for the next great era of life, one that would see the emergence of a new kind of animal, the reptile, and the rise of the great supercontinent that would dominate the next chapter of our planet's story. The Carboniferous period, with its lush, oxygen-rich swamps, couldn't last forever. The slow, patient work of plate tectonics was bringing all the major landmasses together into one colossal supercontinent, Pangaea. This massive landmass, spanning from pole to pole, completely reshaped the planet's climate. The interior of Pangaea was a vast, arid desert, far from the moisture of the oceans. The immense mountain ranges created by the continental collisions, like the ancestral Appalachians, also cast a rain shadow, creating a drier, more seasonal climate across much of the globe. The great swampy forests of the Carboniferous began to shrink and give way to new ecosystems. The change in climate favored a new kind of animal, the reptile. Unlike the amphibians, who were tied to the water for reproduction, reptiles had a crucial evolutionary innovation, the amniotic egg. This was, in essence, a self-contained pond, a tiny portable universe for the embryo that could be laid on dry land. This freed reptiles from the water's edge and allowed them to colonize the vast, arid interiors of Pangaea. They evolved a scaly skin to prevent water loss and more efficient lungs to breathe the air. This single evolutionary step was the key that unlocked the rest of the planet for animal life. The Permian period, which followed the Carboniferous, was the age of reptiles. They came in all shapes and sizes, from small lizard-like creatures to large sail-backed herbivores like Dimetrodon. But just as life was thriving in this new reptile-dominated world, a cataclysm was brewing. The Permian period ended with the most severe extinction event in Earth's history, a global catastrophe known as the Permian-Triassic extinction event, or more dramatically, the Great Dying. It was a devastation on a scale we can barely comprehend. Something like 96% of all marine species and 70% of all terrestrial vertebrate species were wiped out. It was a close call, a moment when life on Earth almost completely reset. The cause of this event is still a subject of intense scientific study and debate, but the leading theory points to a massive volcanic eruption in what is now Siberia. These eruptions, known as the Siberian traps, were not like the volcanic cones we see today. They were a series of fissures in the ground that spewed immense quantities of lava and gas over a period of hundreds of thousands of years. The scale of the eruptions was staggering, covering an area the size of Europe. The immediate effects would have been devastating. The volcanoes released a cascade of toxic gases, including immense amounts of carbon dioxide and sulfur dioxide. This had a dual effect. The sulfur dioxide would have created a brief but intense period of global cooling as it formed aerosols that blocked out sunlight. But the long-term effect was driven by the carbon dioxide. It created a runaway greenhouse effect, a period of dramatic global warming that lasted for millions of years. This warming would have heated the oceans, reducing the amount of oxygen that could dissolve in the water. This led to anoxia, or a lack of oxygen in the seas, which would have suffocated most marine life. A strange and lesser-known fact about this period is the role of methane hydrates. Methane hydrates are a frozen crystalline form of methane that are found in great abundance at the bottom of the ocean. The warming of the ocean is thought to have destabilized these hydrates, causing them to melt and release a massive additional pulse of methane and even more potent greenhouse gas into the atmosphere. This would have amplified the warming and sealed the fate of countless species. This brings up one of those great unanswered questions. How did life survive at all? A small percentage of species, a lucky few, were able to endure the extreme heat, the acidic oceans, and the poisoned atmosphere. They were the ones who would go on to repopulate the planet and give rise to a whole new era of life. Their survival against all odds is a testament to the sheer resilience of the biological tapestry. So as we move from the Permian into the Triassic period, we leave behind a planet that has been scoured clean. The great reptiles of the Permian are gone, and the world is a blank canvas. This is a crucial concept. The very emptiness of this world is what allowed for the next great act of evolution, the rise of a new group of reptiles that would come to dominate the planet for the next 180 million years. This is the dawn of the dinosaurs. The Great Dying left the planet a scarred, barren place, but it also left behind a world of empty ecological niches. The few survivors of the Permian extinction were poised to inherit the Earth. The Triassic period which followed was a time of slow, patient recovery and diversification. The world was still dominated by the supercontinent Pangaea, and the climate remained hot and dry. In this new world, a new kind of reptile began to emerge, one that would come to dominate the planet for the next 180 million years. This is the Mesozoic era, the age of middle life, and it is often called the age of reptiles. The early Triassic was a time of small, unassuming reptiles. But as the world recovered, these reptiles began to evolve into a dazzling variety of forms. Some, like the plesiosaurs and ichthyosaurs, returned to the seas, evolving into streamlined fish-like predators. Others, like the pterosaurs, took to the skies, becoming the first vertebrates to achieve powered flight. But the true kings of this new world were the dinosaurs. They started out small, no bigger than a turkey, but they quickly diversified, filling the ecological niches left vacant by the Permian extinction. The Mesozoic era is divided into three periods: the Triassic, Jurassic, and Cretaceous. The Triassic saw the first dinosaurs, but they were not yet the dominant life form. They coexisted with a variety of other reptiles, including the crocodile-like phytosaurs and the large four-legged dicynodonts. It was a time of great experimentation, a biological lottery where many different groups of reptiles were competing for dominance. Then came the Jurassic period. Pangaea began to slowly, inexorably break apart. This rifting created new coastlines and new inland seas, which led to a more humid climate. The vast arid deserts of the Triassic gave way to lush, verdant forests. The dinosaurs took full advantage of this new world, and their size and diversity exploded. This is the age of the giants. We have the long-necked sauropods, like Brachiosaurus and Diplodocus, which were the largest land animals to ever live. We have the ferocious two-legged predators like Allosaurus, and we have the armored herbivorous Stegosaurus with its distinctive plates and spiked tail. A fascinating, little-known scientific fact is that many dinosaurs, particularly the predatory ones, were not the slow lumbering lizards we once imagined. Evidence such as fossilized trackways and bone structure suggests that many were active, fast-moving, and possibly even warm-blooded. The idea that dinosaurs were cold-blooded, sluggish creatures is a classic misconception that science has largely moved past. Then came the Cretaceous period, the final chapter of the age of dinosaurs. Pangaea had now broken apart into continents that were beginning to look more familiar. The climate was still warm, but the first flowering plants, or angiosperms, began to appear. This was another one of those quiet but monumental revolutions. Flowering plants, with their ability to attract pollinators like insects, were incredibly successful. Their appearance led to a co-evolutionary dance between plants and insects that created a whole new level of biodiversity. The dinosaurs continued to dominate. The Cretaceous gave us the iconic Tyrannosaurus rex, a massive apex predator, and the horned Triceratops, a powerful herbivore. Dinosaurs had conquered the land, the air, and the seas. They had a long and incredibly successful run, a reign that lasted for 180 million years, far longer than the entire history of humanity. This raises an interesting and profound question. Why were the dinosaurs so successful? What was it about their body plan, their physiology, or their evolutionary path that allowed them to dominate the planet for so long? We don't have a single simple answer. It was likely a combination of factors, including their unique respiratory systems, their ability to grow to immense sizes, and their incredible adaptability. Their long reign is a powerful reminder that evolution is not a race to a predetermined finish line, but a long, slow process of adaptation and survival. So, as we reach the end of the Cretaceous period, we see a world in full bloom. The dinosaurs are at the height of their power. The first flowering plants are spreading across the continents, and the stage is set for a climax of unimaginable proportions. The reign of the thunder lizards is about to come to a sudden and violent end, paving the way for the rise of a new group of animals that had, until now, been living in the shadows. The reign of the dinosaurs was a long and spectacular one, but as we know from the fossil record, all great empires must eventually fall. The end of the Cretaceous period, around 66 million years ago, was marked by a cataclysmic event that would forever change the course of life on Earth. This is the story of the Cretaceous-Paleogene KPG extinction event, a sudden and violent end to the Mesozoic era. For a long time, the cause of the dinosaurs' extinction was one of the greatest mysteries in science. Was it a slow decline due to climate change? Was it a result of a massive volcanic eruption? The breakthrough came in 1980 when a team of scientists, led by Luis and Walter Alvarez, discovered a thin layer of clay rich in the element iridium at the KPG boundary. Iridium is very rare on Earth's surface, but is found in much higher concentrations in asteroids and other extraterrestrial objects. This led them to propose a daring and radical hypothesis. The dinosaurs were killed by an asteroid impact. The evidence for this impact is overwhelming. In 1991, a massive crater over 180 kilometers in diameter was discovered buried under the Yucatan Peninsula in Mexico. This is the Chicxulub crater, and its age perfectly matches the KPG boundary. The impactor is estimated to have been a colossal asteroid, perhaps 10 to 15 kilometers across a veritable mountain from space. The energy released by the impact was unimaginable, equivalent to billions of times the power of the atomic bomb dropped on Hiroshima. The immediate aftermath would have been a global firestorm. The impact vaporized the asteroid and a large part of the Earth's crust, sending a massive plume of superheated material high into the atmosphere. This debris, as it re-entered the atmosphere, would have heated up to incandescence, raining down on the planet as a hail of fiery glass. This would have ignited fires across the globe, creating a world of raging infernos. The air itself would have become a furnace. Any large animal caught out in the open would have been instantly incinerated. But the immediate firestorm was just the beginning. The impact also sent out a massive shockwave and triggered a global tsunami that would have scoured the coastlines of the Americas. More importantly, the immense amount of dust and soot thrown into the atmosphere blocked out the sun. The planet was plunged into a period of prolonged darkness, a phenomenon known as an impact winter. Photosynthesis. The very foundation of most food chains would have shut down. Plants died, and the herbivores that depended on them starved. In turn, the carnivores that ate the herbivores also starved. The entire ecological pyramid collapsed. A little known but intriguing fact about this event is that the impact site itself was particularly bad. The Chicxulub asteroid hit a shallow sea rich in gypsum and limestone. These rocks, when vaporized, released a massive amount of sulfur into the atmosphere. This sulfur reacted with water to form sulfuric acid, which fell as acid rain, further devastating the plant life and making the oceans even more acidic. This was a 1-2 punch of unimaginable cruelty, a perfect storm of environmental devastation. This raises an interesting and profound question. Was the extinction of the dinosaurs inevitable? Did their size and specialization make them particularly vulnerable to such a global catastrophe, while smaller, more adaptable creatures like the early mammals were able to survive? The truth is, we don't know for sure, but it is clear that the extinction was not a slow decline, but a sudden and brutal reset. The survivors were not necessarily the fittest in the traditional sense, but often the ones who were lucky enough to be in the right place at the right time, or who had a body plan that was more suited to surviving a prolonged period of darkness and cold. So, as the dust from the impact began to settle and the sun slowly began to shine again, a new world was waiting to be born. The dinosaurs were gone, but a few small, unassuming mammals had survived hiding in burrows, and scavenging in the dark. They were the inheritors of the Earth, and the stage was now set for the next great era of life, the Cenozoic era, the Age of Mammals. The KPG extinction event was a brutal, indiscriminate reset button for life on Earth. But in the long, dark shadow of the dinosaurs' demise, a new story was just beginning. The Cenozoic era, the Age of Mammals, began with a world of opportunity. The ecological niches that had been filled by dinosaurs for 180 million years were now empty. The climate was still recovering, but it was becoming more stable, and the continents were continuing their slow drift toward their modern positions. The mammals that survived the catastrophe were small, unassuming creatures often no bigger than a rat or a shrew. They were mostly nocturnal, living in the shadows of the dinosaurs' world. But they had a few key evolutionary advantages. They were endothermic, or warm-blooded, which meant they could maintain a stable body temperature in a fluctuating environment. They also had a more efficient reproductive strategy, giving birth to live young and nursing them, which gave their offspring a better chance of survival. With the dinosaurs gone, these small mammals began to diversify at an astonishing pace, a process known as an evolutionary radiation. The first 10 million years of the Cenozoic, the Paleocene epoch, saw the rapid rise of new mammalian groups. We see the emergence of early primates, the ancestors of all modern monkeys, apes, and humans. We see the first large herbivores and carnivores, though they were still quite primitive. The world was a patchwork of forests and savannas, and the mammals were adapting to every corner of it. Then came the Eocene epoch, a time of immense global warming. The climate was so warm that palm trees grew as far north as the Arctic Circle. This hothouse world saw the continued diversification of mammals. Many of the modern orders of mammals we know today, such as horses, rhinos, bats, and whales, had their origins in this period. Yes, a fascinating and often overlooked scientific fact is that the ancestors of whales were land-dwelling hoofed animals that returned to the sea. The fossil record of their transition from the wolf-like Pachycetus to the fully aquatic Basilosaurus is one of the most beautiful and well-documented examples of macroevolution. As the continents continued to drift apart, the climate began to cool again. The Oligocene epoch saw the formation of the first permanent ice sheets in Antarctica, and the global climate became drier and more seasonal. The vast forests began to recede, replaced by grasslands. This was a crucial shift, as grasslands created new opportunities for herbivores and carnivores. The first true grazing animals with high-crowned teeth to cope with the abrasive grasses began to appear along with the predators that hunted them. This brings up an interesting question. Was the Age of Mammals an inevitable consequence of the dinosaurs' extinction? Or was it a lucky break-a-chance event that allowed a small marginalized group to suddenly thrive? The truth is, we don't know for sure, but it is clear that the extinction of the dinosaurs was the single most important event in the history of mammals. Without it, we would likely still be living in a dinosaur-dominated world. So, as the Cenozoic era unfolds, we see the world beginning to take on a shape that is more and more familiar to us. The continents are in their places, the climate is becoming more seasonal, and the animals that would eventually lead to our own species are beginning their long, slow march toward dominance. The stage is being set for the next great act of this planetary drama, the emergence of our own lineage, the whispers of a thinking ape. This raises a final and perhaps most profound question. What is it that makes us human? Is it our large brain, our bipedalism, our use of tools, or our ability to use language and to create culture? The truth is, it's probably all of these things and more. The path from a small tree-dwelling primate to a thinking, dreaming, storytelling being is a long and winding one filled with countless twists and turns. It is a story of incredible luck, of relentless adaptation, and of a planet that through its own long and tumultuous history created the conditions for a thinking, self-aware species to emerge. We have journeyed together through a tapestry of time from the first whisper of a nebula to the emergence of a thinking ape. Now we arrive at our own moment, a fleeting instance in a history of billions of years. The Holocene epoch is a name for this last sliver of time, the 700 years since the last major ice age ended. But our story, our impact is so profound that many scientists are now proposing a new epoch, the Anthropocene, the age of humans. This is a testament to our immense power and our equally immense responsibility. For the first time in Earth's history, a single species has become the dominant geological force. We have reshaped the landscape with our cities and our agriculture. We have altered the very chemistry of the atmosphere. With the fossil fuels, we burn fuels that are, as we remember, the sunlight of the Carboniferous and Jurassic preserved in rock. We have driven countless other species to extinction and have moved life around the globe, creating a new interconnected biological world. This is a strange and unique position to be in. We are both a product of Earth's long evolution and the chief agent of its next great transformation. The Earth we live on today is a planet that has been profoundly shaped by our presence. Our fingerprints are everywhere, from the deepest oceans to the highest mountains. This raises an interesting and somewhat uncomfortable question. What will our legacy be? Will we be remembered in the geological record as a brief but destructive force, a blip of chaos and extinction? Or will we be the species that, in its unique capacity for self-awareness and foresight, learned to live in harmony with the planet that gave it birth? The truth is, we don't know for sure. The future is a story that we are at this very moment in the process of writing. And in this final section, I want to leave you with a core scientific concept and a curious fact. The concept is the Fermi paradox, which asks a simple but haunting question. If the universe is so vast and so old, and if the conditions for life are so common, why haven't we found any evidence of other advanced civilizations? Where is everybody? It's a question that has no easy answer, and it forces us to confront the possibility that either we are alone or that advanced civilizations tend to destroy themselves before they can spread across the stars. This paradox is a mirror, and it asks us to look at our own history and our own future. The curious fact is a reminder of our own fragility and our own place in the cosmos. Remember how we talked about entropy, the inexorable march toward disorder. The universe is slowly and patiently unwinding itself. Our sun is a star of middle age, and it will not last forever. In about 1 billion years, as it gets hotter, it will boil away our oceans and make the planet uninhabitable. And in 5 billion years, it will swell into a red giant, engulfing the Earth entirely. Our home, our beautiful, resilient, and life-giving home, is not a permanent fixture. It is a temporary, ephemeral moment in the long-flowing river of cosmic time. This is a humbling, and I hope a deeply comforting thought. We are here now in this brief moment, and that is a truly magnificent thing. Now I'd like to gently ask one last time, where is the place you're staying now? The time in that place, at this very moment, how is it flowing? I want you to feel the quiet stillness of your own space, the long, impossible story we've just told, of dust and fire, of water and life, of dinosaurs and mammals. All of it has led to this exact moment, to you here now. As the echoes of our long journey slowly fade, let your mind drift away from the vastness of space and the crushing weight of geological time. Let your awareness come back to the soft warmth of your bed, the gentle hum of your refrigerator, the quiet breathing of a world at rest. The immense story of Earth's evolution is not just a tale of the past. It's a part of you, a part of the stardust and the living history that makes up every cell in your body. Let that thought comfort you. If you enjoyed this journey, I would be honored if you would consider joining us again next time. But for now, the story is over, and the night has arrived. Sleep well, my companion, wherever and whenever you are. Sweet dreams.